In the landscape of 2026, we have reached a critical breaking point. Despite the Model Context Protocol, MCP, reaching over 97 million downloads and becoming the de facto standard for model-to-tool integration, most enterprise AI initiatives are failing at the finish line. Why? Because while our agents can finally talk to databases and local files via standardized MCP servers, they remain functionally mute when trying to talk to each other. We are witnessing a massive fragmentation where the agentic silo has replaced the data silo. Developers are rushing to implement MCP for its ease of use in connecting LLMs to Google Drive or Slack APIs, but they are ignoring the emergent need for agent-to-agent, A2A, communication protocols. This technical debt is accumulating rapidly. Without a unified standard to govern how an autonomous procurement agent negotiates with a logistics agent, your AI workforce is nothing more than a collection of expensive, isolated calculators. The industry is currently split between the tool-centric view and the agent-centric view, creating a digital Tower of Babel that threatens the very scalability of autonomous systems. We must move beyond simple tool calling and address the architectural void between independent agentic entities. But wait, is the problem simply a lack of a common language, or is it a fundamental architectural flaw in how we define agentic boundaries? I will show you the exact breaking point of these isolated systems and what we will reveal by the end of this lecture to fix it. Building a resilient 2026 roadmap requires sharp surgical distinction. When do you use MCP and when do you move to a full A2A protocol? In the field, we often see architects making the fatal mistake of stretching MCP servers to handle complex agentic handshakes. MCP is designed for model-to-resource connectivity. It is the USB-C of the AI world, providing the transport for context and tools. However, true agent-to-agent, A2A, communication involves state management, permission delegation, and long-running negotiation cycles that MCP was never built to support. For example, if you're designing a system where a customer service agent needs to trigger a refund agent, simply giving them both access to the same database tool via MCP isn't enough. You need a protocol that defines the contract of the handoffs. Your 2026 decision matrix must evaluate the boundary of autonomy. If the interaction is stateless and involves fetching data, MCP is your best friend. If the interaction involves shifting responsibility or shared goals, you must look toward emerging A2A standards like the Agent Protocol or EEEP3327. Choosing the wrong path now means your entire agentic stack will be incompatible with the global AI ecosystem in less than 18 months. This is just the theoretical divide. To understand why this choice determines your system's survival, we must first look at how the entire agentic stack evolved to this point of crisis. In the early days of agent development, integration was a nightmare of brittle, hard-coded REST APIs. Every time you wanted your agent to check a SQL database or a Slack channel, you had to manually write custom function calling wrappers and manage schema mismatches. This API hell created massive technical debt. If the external service updated its documentation, the agent's reasoning loop would immediately shatter. By 2026, we have moved beyond this primitive glue code era. The industry realized that agents shouldn't be hardwired to specific endpoints. They need a universal language to discover and utilize capabilities dynamically. This shift mirrors the transition from manual circuit switching to the standardized TCP/IP protocol. We are no longer just building connected apps. We are architecting interoperable intelligence that can navigate high-dimensional data environments without manual intervention. But if manual APIs are failing, what does the new agentic stack actually look like 2026? Let's peel back the layers in the next scene. The 2026 agentic stack introduces a critical interoperability layer that sits between the core reasoning engine and the execution environment. Think of it as a two-tier system. Layer 1 is the internal reasoning layer, where the LLM processes intent and policy. Layer 2 is the external interoperability layer, where protocols like MCP and A2A act as the glue. In this architecture, the agent doesn't need to know how to talk to a specific CRM. It simply broadcasts a standardized request through the protocol layer, which handles the translation, security handshakes, and data formatting. This separation of concerns allows developers to swap out underlying models or external tools without rewriting the entire logic chain. We are seeing a move toward plug-and-play intelligence where the cost of adding a new capability drops towards zero. However, this modularity introduces new risks in security and latency that must be managed at the architectural level. The stack is ready, but a standard war is brewing between the giants, and the first one to blink is Anthropic. How do they plan to own this layer? We'll see it next. Anthropic's Model Context Protocol, or MCP, has rapidly become the de facto standard for connecting agents to diverse data sources. Why? Because it solved the context fragmentation problem. Before MCP, every agent needed a custom connector for GitHub, another for Google Drive, and another for Postgres. MCP provides a universal interface that allows an agent to see into these systems with a single implementation. It uses a client-server architecture where a single MCP server can serve multiple agents, providing them with real-time access to documents, database schemas, and even local file systems. This doesn't just improve efficiency, it fundamentally changes the agent's worldview by providing a consistent lens through which to observe data. In professional environments, MCP is the key to breaking down information silos that have plagued enterprises for decades. MCP dominates the tool-to-agent connection, but how do agents talk to other agents when business goals clash or collaboration is required? That's where Google's play comes in the AAA standard. While MCP focuses on the connection between an agent and its tools, Google's A2A, agent-to-agent, protocol addresses the complex challenge of inter-agent negotiation and task delegation. In a mature AI ecosystem, you don't just have one agent, you have a swarm of specialists. A travel agent might need to hire a financial agent to handle a complex refund, which in turn might consult a legal agent. A2A provides the semantic framework for these agents to discover each other, verify credentials, and negotiate terms of service without human intervention. It defines how an agent can say, I need this specific subtask done. Here are the constraints and the budget. This is the cornerstone of the agentic economy, where high-level collaboration is prioritized over simple data retrieval. Understanding the boundary between MCP for tools and A2A for partners is the most critical skill for a 2026 system architect. MCP for tools, A2A for partners. But how do they look under the hood? In the next chapter, we perform a technical deep dive into the protocols themselves to see which one fits your specific use case. To understand why your AI systems might fail, we must dissect the interface contract of these protocols. The Model Context Protocol, or MCP, acts as a standardized sensory organ for a single LLM. It focuses on tool schema definition, telling the model exactly what a tool can do through structured JSON schemas. In contrast, agent-to-agent or A2A communication is about intent negotiation. While MCP defines a strict function call structure to prevent argument hallucination, A2A protocols like the Agent Protocol or FIPA SEL-inspired frameworks focus on the semantic meaning of a request. In A2A, agents don't just execute functions. They negotiate goals, which requires a much more flexible and descriptive communication layer than a simple tool schema. If you use MCP where A2A is needed, your agents will struggle to understand why they are collaborating. But wait, if they speak such different conceptual languages, how do they actually travel across the network physical layer? Let's get technical with the transport layer. MCP is designed for speed and local efficiency, heavily utilizing JSON RPC 2.0. In most current implementations, like those seen in Cloud Desktop or local IDE extensions, MCP communicates via server-sent events, SSE, or simple standard input-output, STIO. This makes it incredibly lightweight for connecting a local database to an LLM. On the other hand, A2A communication usually demands high durability transport. Because agents might reside in different cloud environments, A2A protocols often leverage gRPC for performance or message brokers like RabbitMQ and Kafka for asynchronous persistence. This difference in serialization lightweight JSON RPC for MCP versus robust, stateful messaging for A2A dictates your system's total latency. Choosing the wrong transport can lead to a 500 ms delay in every single agent hop. Speed is one thing, but how do these protocols remember what happened 2 minutes ago during a complex task? In the world of distributed systems, state management is the ultimate tiebreaker. MCP is fundamentally stateless. Each tool call is a discrete transaction. The LM provides the brain and the memory, while the MCP server simply executes the command and returns the result. It doesn't care about what happened in the last call. A2A communication, however, requires stateful multi-turn negotiations. Two agents must maintain a shared understanding of the conversation, ID, and dialogue state to reach a consensus. If an agent A asks agent B for a budget approval, and agent B asks for clarification, they must both track that specific thread of logic. Failing to manage this state leads to agent dementia, where the system loops indefinitely. This stateful via stateless nature is why MCP is perfect for tools, but A2A is mandatory for complex workflows. We've seen the DNA, but how do these protocols actually perform when you put them under heavy production load? When moving from a POC to a production environment, throughput and reliability become your primary metrics. In recent benchmarks, MCP integration shows almost zero overhead for data retrieval tasks because it maps directly to the model's native tool calling capabilities. However, when you string multiple agents together using A2A protocols, the overhead increases exponentially due to the handshake and verification steps required between agents. A complex workflow involving 5 agent hops can see a 30% drop in reliability if the protocol doesn't support robust retree logic or timeout management. Reliability isn't just about it works. It's about whether the protocol can handle a partial failure of one agent in a chain. MCP excels in one-tool reliability, but A2A provides the failover mechanisms needed for larger swarms. Is this just theoretical, or are the giants of the industry actually using this in production right now? Validation of these standards comes from the engineering leads at the forefront of AI. Anthropic's team, the creators of MCP, emphasizes that the protocol is designed to solve the context silo problem, allowing models to access real-time data without custom glue code for every API. Meanwhile, researchers at Google and contributors to the AutoGen project suggest that A2A protocols are the internet protocol for a future society of agents. They warn that without standardized A2A, we will face an agentic lock-in where agents from different vendors cannot collaborate. The community consensus is forming: use MCP for immediate tool integration, but keep an eye on A2A for your long-term multi-agent ecosystem. Now that you understand the technical friction between these protocols, it's time to build the ultimate architecture. The hybrid blueprint is up next, and it is where we combine both for maximum power. In the 2026 enterprise landscape, a single protocol is rarely enough. Consider TreeSoup, a sophisticated news bot case study designed for the Korean market. This system must fetch real-time financial data, summarize it, and deliver it via KakaoTalk. Here, we see the hybrid blueprint in action. The Model Context Protocol, MCP, acts as the hardware tool abstraction layer, allowing the bot to connect to the Kakao messaging API and local SQL databases using a standardized server-client model. Meanwhile, agent-to-agent, A2A, protocols handle the orchestration layer. When a user asks for a summary of today's semiconductor trends, the primary agent doesn't just call a function. It communicates with a specialized analyst agent via A2A to determine the best reasoning strategy before ever touching a tool. By using MCP for tool access and A2A for logic routing, TreeSoup avoids the monolithic agent trap where one LLM tries to do everything and fails. This separation of concerns is the cornerstone of scalable architecture. But how exactly does the data flow between these layers when a user sends a prompt? Let's trace the signal from the user's screen to the protocol wrap tool execution. Visualizing the interoperability flow helps us understand the lifecycle of a modern AI request. The process starts at the user prompt, but the complexity lies in the protocol wrap. Instead of the agent speaking directly to a database, it sends a request to an MCP client. This client then communicates with an MCP server that provides a schema-validated toolset. Simultaneously, if the task requires multi-step reasoning, the agent initiates an A2A handshake. Think of A2A as the management meeting and MCP as the toolbox. In our blueprint, the A2A layer ensures that the agents agree on the goal and the budget token limits, while the MCP layer provides the physical means to act on the world. This multi-layered flow prevents prompt injection from directly hitting your database because the MCP layer acts as a semantic firewall. If you ignore this separation, your system becomes a spaghetti of custom integrations that fail as soon as one API version changes or a new agent is added to the workforce. This architecture allows for true modularity. But what happens when these two protocols need to talk to each other directly through a mediator? We need a bridge to handle the translation. To achieve true scalability in 2026, we introduce the protocol gateway middleware. Many legacy systems within major enterprises still operate on REST or SOAP, which don't natively understand MCP or A2A protocols. The gateway acts as a vital translator and orchestrator. On the southward side, it wraps legacy database procedures and internal microservices into MCP server definitions, exposing them as standardized tools. On the northward side, provides an A2A interface, allowing external or internal agents to query these tools as if they were talking to another intelligent agent. This architectural pattern is essential for agentic governance. It ensures that every data access request is audited, rate-limited, and authorized at the gateway level regardless of which protocol is used. We use this tech stack to maintain security boundaries while providing the flexibility of modern AI interoperability. It's the only way to modernize without a complete rip and replace of your existing IT infrastructure. However, high concurrency environments introduce a new set of problems. What if the MCP server is ready, but the A2A agent is busy? Conflicts are inevitable in a distributed agent world. In a high concurrency agentic ecosystem, protocol conflicts are the silent killers of system performance. When multiple agents attempt to access a single MCP-wrapped tool simultaneously through different A2A channels, face classic race conditions and distributed deadlocks. To resolve this, we must implement lease-based access within the protocol gateway and define retry policies that are protocol-aware. For example, an A2A timeout should be handled with a different backoff strategy than an MCP connection reset. We also need to address state consistency, ensuring that if an A2A agent fails halfway through a multi-step tool execution, the MCP server can roll back the state or notify the supervisor agent. This FAQ addresses the most critical friction points architects face when merging these protocols. Mastering these edge cases is what separates a fragile prototype from a production-ready enterprise agent system. As we've seen, the blueprint is complex, but the real danger lies in what happens when these boundaries are crossed by unauthorized actors or proprietary lock-ins. In the next chapter, we'll dive into the shadows of this architecture, risks, lock-in, and the fragile boundaries of trust. In the world of technology, open is a word often used as a marketing shield. While protocols like MCP aim for universal interoperability, we must address the hidden reality of the standardization war. History shows that whoever controls the core specification of a protocol eventually dictates the ecosystem's direction. If your entire agent architecture is built solely on one vendor's implementation of MCP, you aren't just adopting a standard, you are inheriting their roadmap, their limitations, and their pricing models. We call this protocol-led lock-in. Even if the code is open source, the gravity of the ecosystem, the plugins, the specialized tools, and the community support can create a wall that makes switching to a competing A2A standard like the ones proposed by OpenAI or Google extremely costly. As an architect, you must evaluate if your chosen protocol allows for exit-friendly designs, or if it creates a proprietary trap disguised as a bridge. The illusion of freedom often masks the chains of dependency that manifest 2 years down the line. But wait, protocol lock-in is only half the battle. How do we handle the data that flows through these pipes without losing control? From the perspective of an information management professional, the most terrifying aspect of the 2026 agent landscape is the erosion of the trust boundary. When an internal agent uses an A2A protocol to consult an external market research agent, data egress becomes a silent, automated process. Traditional firewalls and DLP systems are not designed for the semantic nature of LLM communications. We are moving from a world of IP-based security to context-based security. If an MCP-connected tool has access to your local database, any prompt injection vulnerability in the connected agent could lead to a massive data leak. You must define clear data perimeters where agents are categorized by their clearance levels. We need to implement semantic gateways that scan the intents of agent messages before they cross the organizational boundary. This is not just about encryption, it is about ensuring that private business logic isn't leaked through the chain of thought shared between agents. But here is the question: how do we quantitatively decide which external agents are safe enough to talk to our most sensitive systems? To manage the risk of third-party integration, we require a systematic trust scoring mechanism. In 2026, you shouldn't connect to an agent simply because it follows the A2A protocol. You connect because it meets a predefined reliability threshold. This checklist represents the information management professional's due diligence for the AI era. We must verify the identity of the agent through decentralized identifiers, the IDs, and check for a history of safe execution. Does the agent have a verifiable safety policy? Is the vendor providing a bill of materials for their agent's training data and guardrails? This reliability check is the difference between a secure enterprise system and a fragile prototype. As we conclude this chapter on risks, remember that security is not a one-time setup, but a continuous monitoring task. Every connection is a liability unless proven otherwise through strict governance. Now that we have faced the dangers of lock-in and security breaches, let's move to our final chapter to synthesize these lessons into a winning 2026 strategy. As we stand at the threshold of 2026, the choice between MCP and A2A protocols is not a binary decision, but a strategic layering of capabilities. Think of the Model Context Protocol, or MCP, as the universal USB-C port for your AI models. It is the essential interface for connecting diverse data sources and specialized tools without writing custom integrations for every new vendor. On the other hand, agent-to-agent protocols act as the diplomatic language for cross-organizational collaboration. In your decision matrix, prioritize MCP when building internal tool-using agents to maximize resource reuse and reduce latency. Shift your focus to A2A standards when your architecture requires complex negotiation, state sharing, or transactional integrity between autonomous entities. A hybrid approach often yields the highest ROI, using MCP for the muscle of tool execution and A2A for the brain of strategic coordination. But remember, the technical choice is only half the battle. The real risk lies in how you manage the trust boundaries across these connections. Is this architectural map enough to guarantee success? Not until we look at the ultimate competitive edge that will define the leaders of 2026. The ultimate competitive advantage in the 2026 Agentic era will not belong to the company with the largest model, but to the one with the most interoperable ecosystem. We are moving away from monolithic AI silos toward a fluid, networked economy of agents. Your strategy must focus on three pillars: modularity, observability, and standard compliance. By adopting open protocols like MCP today, you ensure that your infrastructure remains agent-ready regardless of which LLM provider dominates the next cycle. Avoid the trap of proprietary wrappers that promise convenience but deliver long-term vendor lock-in. Instead, architect your system so that switching an underlying tool or a collaborator agent is as simple as updating a configuration file. This level of agility is what will separate the industry leaders from those struggling with mounting technical debt. The era of isolated AI is over. The era of the interconnected, autonomous workforce has begun. This concludes our guide on 2026 agent interoperability, but your journey into architecting these complex systems is just starting. Now that you have the blueprint, what will be your first move in this new interconnected landscape?